So today we're just going to take that same idea of optimization, finding that either the best max or the best min, depending on what it says, using our calculus to do that, just applying it to economic situations now instead of applying it to geometric situations. So we've talked about some things in economics already. So let me just review with you the different functions that we have. Okay, you have C of x, which is always referring to the cost function. We have R of x, which always refers to revenue. We have P of x, which refers to profit. And how does P of x relate to the other two? Right, it's your revenue minus your cost. Okay, profit is always revenue, the money that you're taking in, subtract cost, which is the money that you have to spend. And so then you've got profit. We have already talked about the meanings of C prime, R prime, and P prime. Does anybody remember what prime means in economics? Marginal, okay, or instantaneous. And so we call it the marginal because it only works for a margin. It's for just marginal means you're only working just for the very next one, the item that comes right after that. So it's a marginal or instantaneous cost. And then you've got prime defined as all the other ones. You've got marginal revenue, which is the revenue for the very next item, or marginal profit, which is the marginal profit for the very next item. So the word optimize or max or min can be applied to any of those. If they say find the max cost, you'll take the derivative of the cost and solve it. If they say find the maximum marginal cost, then you're going to take the derivative of the derivative that you already have. So it's a double derivative. So watch the words so that you know what you're starting with and what you're supposed to take the derivative of. So there's a third thing that I need to make sure you understand, which is this symbol with they call it bar. C bar, R bar, P bar. And this is the symbol for average cost, average revenue, and average profit. Average, you've seen before, we've talked about it being secant. So average is C of x minus C of 0 over x minus 0. Or C of b, like y2 minus y1 over x2 minus x1. It's over a long period of time. The difference between marginal is that it's an instantaneous moment. Average is over a long period of time. And so all of these are defined the same. So you'll have R of x minus R of 0 over x minus 0, and then P of x minus P of 0 over x minus 0. So that's just the definition. And so then they say optimize the average cost. Well, then you start with that function, and that's what you take the derivative of. So when you're reading these homework questions, you just got to make sure you're reading carefully. Am I starting with regular cost? Am I starting with marginal cost? Am I starting with average cost? Whatever they're referencing, you start with that, and then that's what you apply the derivative to. Even if you've already applied the derivative to get to marginal, if it says to optimize it, you're going to have to do the derivative again. So here's some examples of how that would work. So here's a company. The company has R of x, their revenue, as 9x. So they're getting $9 or $9,000, whatever, for every unit. Their cost equation is x to the third minus 6x squared plus 15x. And the question is, what production level, how many x's will maximize their cost? Excuse me, maximize profit. That's what we want to do. We do not want to maximize cost. All right, so if you're starting with your revenue defined as 9x, you know that your cost is defined as a cubic function. What production level will maximize your profit? And so because we're maximizing profit, we need to define a profit equation, and then we need to apply the principles of maximization to that. So we'll come up with P of x. We know that P of x is defined as revenue minus cost, the difference between the two. So this will be 9x minus the quantity x cubed minus 6x squared plus 15x. And when we subtract, you need to make sure that you distribute that negative. So 9x minus x cubed plus 6x squared and minus 15x. So our overall profit equation is a negative cubic function, negative x cubed plus 6x squared minus 6x. Once we have the profit equation, we know that we're supposed to maximize that. So we apply the calculus principles of maximization, which would be to take the derivative, set that derivative equal to 0, and look for the points of maximization. So now we'll take optimize, and so we'll take P prime. P prime will be negative 3x to the second plus 12x minus 6, and we'll set that equal to 0. I'm going to factor out a negative 3. That'll leave me with x squared minus 4x plus 2, which does not factor, which means I need the quadratic formula. So I'm going to x equals 4 plus or minus 16 minus 4 times negative 3 times 2 all over negative 6. So 4 plus or minus 16 plus 24. So that'll give me 4 plus or minus the square root of 40. Oh, yeah. I was looking at my a that I'd taken out. I was looking at my a of the original function instead. Thanks for catching that. So that can just be a 1. So let's clean that up a little bit. And then also my denominator doesn't need to be that, because I'd already factored it out. Okay, over 2, 1, 16 minus 8. Okay, better. All right, that gives me two solutions. They are 0.586 and they are 3.414. So we get two viable solutions. If one of them had turned out to be negative or something, we'd know clearly that was not the answer, because you can't have negative production. Okay, but these are two viable possibilities. And so I need to decide which one of these two is going to be producing my maximum production level. So I can either check for a change from positive to negative in the first derivative, or I like to check the second derivative and check the concavity. So I'm going to go back and look at what my second derivative is. So my p double prime for this problem will be negative 6x plus 12. To me, that's a pretty simple concavity equation. And I can check what the values of p double prime of 0.586 compared to p double prime of 3.414 are. So negative 6 times 0.586 plus 12, that's going to give me a positive number. And negative 6 times 3.414 plus 12, that's going to give me a negative number. So based on concavity, I want negative concavity, because negative concavity to me means a positive, it means a maximum. Okay, negative concavity is the one that's going to be the max. The positive concavity is the one that's going to be the min. So the production level that you want to recommend to your boss or your manager or your employer, okay, I got it. We need to produce at a level of 3.414 of whatever we're making, and that's going to maximize our profit. Okay, and you'll be the hero. Again, nice bonus Christmas check for you to take home. Okay, any questions about that one? Okay, so if you want to maximize profit, what might be something in economics you'd want to minimize? Okay, so let's do one where we're going to minimize cost. All right, so let's look at a cost function. So let's say C of x is the cost function determined by x cubed minus 6x squared plus 15x. And your situation is to minimize the average cost. Not the total cost, but the average cost. So we are not taking the derivative of the cost function as it is. We have to make it into an average cost function first before we take the derivative, before we apply the minimization strategy. So I need to come up with my C bar. C bar is C of x minus C of 0 over x minus 0. So in this case, C of x is x cubed minus 6x squared plus 15x. And then C of 0 is 0, so minus 0, over x minus 0, which is just x. So when I subtract 0, that's not going to affect my numerator at all. So I think I'm just going to get rid of it. And so my equation simplifies. I reduce by x, and my C bar equation is x squared minus 6x plus 15. That's just C bar. Now I want to minimize C bar, minimize the average cost. So now I'm going to do C bar prime, which will be 2x minus 6. Set that equal to 0. X is 3. But you want to really make sure that that is a minimum. And so I like to check the concavity to make sure it's going to be a minimum. So to check the concavity, I'm going to do C bar double prime. And the second derivative is just the number 2. The number 2 is constant. That means it's going to be positive concavity. So the number 2 implies positive concavity. Positive concavity implies that it's a min. And so I can rest a little easier knowing that, okay, phew, I have a minimum. I found my minimum. All right, so again, hey boss, to minimize our cost, we need to be working at x equals 3 units. Or minimize our average cost. Okay, so then we haven't really talked about endpoints here because you were bringing that up for your homework. All right, the endpoint for here is going to be x greater than 0, right? There is no maximum for the endpoint. There is but I mean, clearly we're not going to use negative numbers. So if there was none, then you just might say, this is not a good idea, and we should not be making this item at all because we can't, our costs will never be minimum. Okay, it's not going to be worth it. Okay, so then you'd have to maybe come up with well, this is not a good business for me to be in. Yeah, okay.
What is a production level of 3.414?
Okay, that's really, so a lot of times these things, I mean, you're talking about a company that's measuring things in the thousands. Okay, so 3.414 thousand of something. Okay, so 3.414 thousand units. So that would really be 3,414 units of whatever they're making. Or maybe they're measuring things in the millions and they're going to be producing 3.414 million whatever they're making. Okay, Apple Pencils or whatever their company is designing. I mean, we're not talking, this is not like your mom and pop little organization that's on Etsy that's making, 3 little craft things every month. These are big old companies so the units are on a large scale.